Okay, so this very sheet is going to be on your exam, and you're going to write out definitions in your own words for these sheets on Monday's exam, or for these questions on Monday's exam. So let's look at Chapter 7. So Chapter 7 was our sampling distribution of the sampling mean. So that was one of the questions I asked. Anyone can describe what the sampling distribution of sampling means is? This is basically the whole test is based on this. The whole test is based on these sampling distribution of sample means. We did confidence intervals, we used this. When we did hypothesis test, we used this. So what is it? What is a sampling distribution of sample means?
Is it from like the sample that we grabbed or pulled, the average of the sample that we used?
All right, but a sample is not a number, right? The average of what?
I guess the average of what we used as like I can't explain it. I'm sorry.
Because a sample is an object, right? So we take a sample from population, and then we take another sample, okay? And so what are we doing? So we have all these samples. What is the sampling distribution of sample means?
The average of the samples?
Okay, but again, a sample is an object. You can't. That's like saying take the average of the people in this class. It doesn't make sense, right? What do you take an average of? You take an average of values. So what values are you taking the average of from those samples? You can't average samples. A sample is a group. It's like an object. It's like saying what's the average of all the items on this desk, right? That doesn't make sense, right? That's the same thing as saying what's the average of the samples. So what is it about the samples that we're taking the average of? What's that? Whose lips are moving? Oh. Right, we take the mean of all these samples, and then what do? We've got a mean from sample 1, and then a mean from sample 2, and a mean from sample 3, and a mean from sample 4. We have all these means. Well, now that just became what those means are called. What are those? No, just the means themselves. That's a random variable, because each sample gives us a different value of a mean, right? So that's a random variable. Blank stares. So what is the sampling distribution of sample means? Okay, that's part of it, right? So the average of the means is part of it. And then what else? It's the distribution. So yeah, so we're going to take the means of all these samples and we're going to have a distribution out of it. And then what is the distribution? It consists of a mean. So it's the mean of the means of the samples, right? It's the mean of the means of the samples. And then what else in the distribution? Standard deviation. So those means will have those means of the samples will have a mean and will have a standard deviation. So remember the basketball example. We took samples of different sizes. So like the basketball, there was 5 people on the team, and we took samples of size 3, and here are the means of each sample of size 3. And so that's a distribution. It's a distribution. It's looking at all the data, variable on the x-axis, frequency, right? The distribution shows variable this way, right? Lowest to highest. And then frequency, up and down, right? Frequency, and we get these curves, right? So distribution is showing how the values of the random variable played out, how they're distributed. Okay, so here let's do baby weight. Okay, this paper, Our Baby's Normal, focused on birth weight of babies. According to the article, the mean birth weight is 3369 with a standard deviation of 581 grams. Okay, so let's go through our questions for this. Is there a random variable involved in this? And what is the random variable? Is there a random variable involved in this? And what is it? He wants weight of babies. Yeah, that's the random variable. We're going to go to baby number 1. And what are we going to do? Look at its weight. And then we're going to go to baby number 2. And we're going to get the value of the variable just changed, right? So it took on the variable took on a certain value for the first baby, but then for the second baby it took on a different value. You see? And then for the third baby it took on a different value. So the random variable is weights of babies. So every real world problem that we've looked at in this class has involved a random variable, something that we're going to go from one thing to the next and capture that value, right? We go from one thing to the next and we get a value. That's called an observation. Okay, what was the next question on the list?
What is the distribution of a random variable?
Okay, so distribution means that if we think of the graph, the representation, what's horizontal? Distribution, right? What's on the horizontal axis? What am I showing here? What's that? Which values? Birth weights, right? Birth weights, the value of the variable, right? The value of the variable goes here from lowest to highest. And then we get some kind of distribution, right? Lots of the ones we've looked at have been normal. And earlier in the course we talked about skewed distributions, right? They're not all normal. So then what is the height of the curve? Frequency, right? This says that like most baby weights would be in a certain range. There are a few babies that have higher weight, and then there's a very few that have a very high weight. Low weights are over here, right? So low to high weights, most babies fall in a certain kind of range. You know? Oh, you had a baby. How much does it weigh? 19 pounds. Right? So where's that? So it's like maybe it's happened, right? But so it'd be way out here, right? A high value, but very infrequent. How much did your baby weigh? 6.5 pounds. Oh, that's so wonderful, right? 6.5 pounds. So lots of babies might be born at 6.5 pounds. High frequency, right? Okay, what's the next question on the list?
Well, there's a two-part to that.
Yeah, go ahead.
Values characterize a particular distribution.
All right, what values characterize a particular distribution? Daisy? The mean is standard deviation. And what is the mean about? What is the mean? We have a mean of 3,369 grams. What does that mean? And what does that mean? What do you mean, average birth weight? Okay, so that's the mode. So it's not necessarily the most frequent, but it's related to that. No, haven't talked about that yet. We're just talking about birth weights. What is the average? Okay, approximate middle. Okay, so it's like what you would expect for the value of the variable. It's like if you were to pick one number, so like here, another baby's going to be born. What would you guess for that next baby? What would you expect? The best you could guess is the mean. Like it's the typical value, right? It's the center of the data. It's the typical value that you would expect. So the mean is a value of the variable. Okay, what is a standard deviation? So this standard deviation is 581. And what does the value of standard deviation indicate? This is on your test. You're going to be writing all this stuff on your test. Yeah.
What does standard deviation mean? How far above or below the mean?
Okay. Yeah, that's how we use it. We use it to look that far, so how far above and below. But for instance, how would the distribution be different if this was 200 grams or 581 or 1,000 grams? What does that number indicate about what's going on?
It's like the range from the average while still being relatively close to the average.
Okay. Yeah. So it's indicating how spread out the data is. How spread out the data is. If this is a low number, then the data is very spread out or not spread out at all. That's a low number. It's all crunched around the mean. A low number means a low spread, that all the data falls really close to the mean. And if it's a really large number, If you have a big standard deviation, what does the curve look like? What's that? Way stretched out and flat, right? So our data is spread out over lots of values. So this is a high standard deviation, right? Because the data is spread out around a big range of values. So the standard deviation is a number that indicates how spread out the data is. A low value means it's all crunched together, very consistent, right? A high standard deviation means the data is way spread out, it's very erratic or inconsistent, right? Okay. So we did the variable is birth weights, and we talked about the distribution, the mean, standard deviation. Okay, so now we have samples of size 200. And if we're talking about a sampling distributions of sample means, what are we doing with our samples of size 200? All right, everyone get a partner and answer that question. We're going to take samples of size 200 babies. So we'll take 200 babies here, 200 babies here, 200 babies here, 200 babies here. What are we going to do? What's the sampling distribution about? Go. No, I'm asking about the sampling distribution of sampling means. I want you to define the sampling distribution of sampling means. What is it about? What is the sampling distribution of sampling means? Go.
We're just explaining it.
Okay. What is it? Tell me. What's the sampling distribution of sample mean? Yes, you. I forgot your name. No, in the corner. Gray shirt. Male. Right, that's our problem. You gotta engage, right? So it's totally useless to have a course where all you do is learn how to do problems, right? This is useless. It just means nothing. Oh, when I see this kind of problem, I do this. And then you walk away after the last day of class and there's no value to that, right? So let's know what we're doing. Let's know what it's about. Okay, you're smiling. So tell me, what is the sampling distribution of sampling means? Yeah. Okay, how about in the back? Okay, so I explained it earlier in class. Mackenzie, how about you? What's the sampling distribution of sampling means? Okay. Okay, everyone listen. Here we go. We got a population. I'm going to take a sample of size 200 here. I'm going to take a sample of size 200 here. I'm going to take a sample of size 200 here. I'm going to take a sample size 200 here. And what I'm going to do for each of those samples? Find the mean. I'm going to find the mean of this sample, and the mean of this sample, and the mean of this sample, and the mean of this sample. Now I have a bunch of means. What am I going to do? Make a distribution of those means, right? One of these. So instead of just the values of the variable, it's going to be values of means of samples. That's what the variable is going to be. Means of samples. Sample 1 mean, sample 2 mean, sample 3, sample 4 mean. So we're going to find the mean and the standard deviation of those sample means. Explain to the person next to you. Go. Everyone explain to the person next to you. Go.
distribution of all samples.
Okay, what will the mean of the means be? What will the mean of the means be? The same as the population mean, remember that? So we'd write this. Where's my pen? We write this. This is what? This is the mean of the means. The mean of all, if we were able to take every single sample and get the mean of those means, we're going to get the population mean. It should make sense. And then what's the standard deviation of the population means? Okay, so that's what it means. Good. So that's how spread out the sample means are, right? And remember when we say we took bigger samples, what about the spread of the sample means? For bigger and bigger samples, it gets more and more spread out. Is that right? No, it gets smaller, right? Because when you take bigger and bigger samples, your means are more likely to be closer to the population mean. So when you take small samples, that you have the possibility of getting outliers, like 2 really high ones or 2 really low ones. Like if your sample size is 2, it's very possible to get like 2 really high ones, 2 really low ones. But if you take larger and larger samples, then the mean is going to much more likely be close to the population mean. So then as the sample size goes up, the standard deviation goes down. You get more consistent means around the population mean. How do we calculate it? We've been doing it in like every problem for the last 3 weeks. This is that. So right. So we take this population standard deviation, divide by, right? We've been doing that for everything, right? We've been doing that for everything. So this is our sampling this characterizes the sampling distribution of sample means. It has a mean and it has a standard deviation. Got to get this principle. Why? Because it's the total, it's the basis of all the confidence intervals we did and all the hypothesis testing we did. We use this for the whole thing.
Can you explain about the small standard deviation of the means and the large ones, like what it means?
What's that now?
You were talking about how big or small the standard deviation is.
Okay.
And what I feel like what it does, like it gets closer to the mean, or
Yeah. So just basically the standard deviation, or related to a sampling distribution.
the sampling.
When I was talking about the sample size, that thing. All right. There's an example here. Any more questions about the baby weight example? Okay. So let's go back. So here's. There's a good slide here. Here we go. So this is, there's 5 people on the basketball team, so we're going to do a sampling distributions. This is the sampling distribution for samples of size 2. So we took 2 players and took their average. Another 2 players took their average. Another 2 players took their average. Mean. So those are those means. Those dots are the means. So what's going to happen now if I take samples of size 3 players and do the distribution of their means? Is it going to get more spread out, or is it going to get crunched closer together? Why? Because there's more so the larger your sample, so now this is the means of samples of size 3. The larger your sample, the more likely that mean will be close to the actual mean. Because there's less of a chance, with a bigger sample, there's less of a chance that you get all really big values or all really small values. Does that make sense? So now I'm going to take samples of size 4 out of those 5 players. So what happens with the larger and larger sample size is the means are going to get closer and closer to the population mean. So the standard deviation of the means goes down. Did it help? Okay. And of course, if you took a sample of size 5, there's only one sample of size 5, all of them, and that mean is the population mean. Okay, so let's move on to more stuff here. Again, this is showing the same thing. When you take a larger sample size, your standard deviation goes of the means. The standard deviation of the distribution of means goes down, right? So here's just, this is, so what's the, okay, so let's go through your list of questions. This is normal distribution for IQs, sample distribution for sample means for size, sample sizes of 4, sample size of 16. So let's go, just take a couple minutes, go through the list of questions from the beginning of class, and answer those questions in this context. Go.
Numeric IQs, the numbers of the IQs. So, we're taking random variables of the IQ and finding out mean and the standard deviation. And we're mapping it out on the normal curve. The variables, the IQs are on the horizontal axis, and the distribution of the standard deviation on the frequency of their mean and variables. You kind of lump it all in one big one. Well, we characterize the distribution of the mean and the standard deviation.
Okay, so could you explain what this, the meaning of this graph is? What is that graph showing? What is it representing? Somebody new. What's that?
A sampling distribution of sample sizes of 4.
Okay, he said a sampling distribution of sample sizes of 4. Okay, so we take samples of size 4, and what do we do? What did we do?
Find the averages of those samples and plot them into the...
Good. So it's just saying take samples of size 4, and what are we looking at in these samples? What is it? What's our random variable? IQ is the original. We firstly IQ is our random variable. Okay, IQ is our random variable, and so then we look at samples of size 4, and then what's our random variable? So we look at samples of size 4, and we have a new random variable. What's the new random variable? The averages of samples of size 4. Right. We're going to take the mean of every sample of size 4, and that's going to be our new random variable. So, for this distribution, the random variable is means of samples of size 4. Mean IQs, right? So mean IQs, or mean IQ. It's the mean IQ of samples of size 4. That's our random variable for that distribution right there. So these numbers down here are these IQs? What are these numbers down here? They're mean IQs. They're average IQs for samples of size 4. They're average IQs for samples of size 4. And then what is this curve showing? The distribution, or the frequency of the different means, right? So 68, a mean of 68. High frequency or low frequency? 105. high frequency, right? High frequency for 105 or something like that. Okay, and by taking samples of size 4, these means when we take a sample of, so here's the original IQ variable. We take a sample of size 4, you know, most likely we're going to get a smattering, right? We're going to get like one here and one like red. Like we're going to get like one there and one there and one there and one there. And when we take the mean of that, it's going to be close to what? Which is what? What's the population mean of IQs? 100. So when we just take a random sample of size 4, what do we say? The mean is going to probably be pretty close to 100. Closer than the original distribution. That's why what happened to the sampling distribution for size 4, it got smaller. Because that variable is for means of samples of size 4, which will more likely be close to 100 than the original just IQs would be. Right? Because we're taking an average of 4 of them. And that's why it got narrower and taller. Take bigger samples, now your samples are really going to be close to 100 on the average. So now here, this is the same thing for samples of size 16. And so those means are much closer to 100 for a larger sample size. Okay, what is the standard? Oh, we don't know. Oh yeah, so how did they get the 8? So where did the 8 come from? Where did the 100 and the 8 come from? Go, tell the person next to you. To get that distribution of sample means, where did the 100 come from? Where did the 8 come from? Where did the 100 come from? What does the 100 mean? What's that? Which mean? Right. The mean of a sampling distribution is the same as the population mean. So it just came right from there, right? That's this thing of that the mean of the sample means is just the mean. So that's that. And what about the 8? Standard deviation of the sample means. Where did it come from? Okay, so it's a measure of the spread of our sample means. And where did that number 8 come from? The population standard deviation divided by square root of the size. Square root of the size. That's where that 8 came from. So that's this. So we took 16 divided by the square root of 4, and we got 8. So this 108 are the numbers that characterize this distribution of the means of samples of size 4. Mean IQs, right? Mean IQs. Okay, let's keep going. So we said that if you have a sample of size 30, it doesn't matter what the initial distribution is, it will become normal. But if you have a normal distribution to start with, all sampling distribution of means will be normal. Remember this? So as we took larger and larger samples of any distribution, it starts becoming normal. But if the original distribution is normal, you don't need a large sample. All of them will be normal. Remember that principle? This is called the central limit theorem. Central limit theorem says, doesn't matter what your initial distribution is, when you take a sampling distribution with a large enough, 30 or bigger, you essentially will get a normal distribution. But if you started with a normal distribution, you don't need a large sample. You don't need a large sample. Any sample size will give you a normal distribution. That's the central limit theorem. Okay, let's just do one of these, and we'll go on to confidence intervals. So let's see. Let's try poverty and dietary calcium. Let's see. So remember, the whole point of this is that there are what? There are two distributions happening in these problems. There's the population distribution. That has a mean and a standard deviation. And then we're going to make a new distribution out of what variable? The means of samples. That's a new distribution. So you got to keep track of which is which. So, and then can you use your z chart to evaluate one or both of those distributions? So let's do this. So let's see how this goes. Okay, so calcium, the recommended adequate intake of calcium is 1,000 milligrams per day. If adults with incomes below the poverty level have a mean calcium intake equal to the RA, what percentage of all samples of 18 such adults have a mean calcium intakes of at most 947 milligrams? Assume that sigma is 188. Okay, so there's an inference of two different distributions here. What is one of the distributions that's in play here? What's one distribution that's in play here? It's two different distributions in play. What's one of them? What's that? The sampling distribution, the distribution of sample means. Okay, so we're going to take samples of size what? Samples of size 18. And we're going to get the sampling distribution, which consists of the mean of the means and the standard deviation of the means. What's the other? And so what's the random variable for that? What's the random variable for that distribution? What random variable are we talking about? What random variable makes up this distribution?
1,000 milligrams. And
What's the random variable? No, 1,000 milligrams per day is not a random variable. It's the random variable. It's the thing that we're putting on the x-axis. If we're gonna draw a picture, what is the thing we're putting on the horizontal axis for this distribution? Mean calcium intakes for samples of size 18. Good. Well, we got there eventually. Good. Without my help. Mean calcium intakes for samples of size 18. Okay, so that's actually the harder. There's another distribution at play, and that's the easier one. What's the other distribution at play here? What's the random variable for that distribution? No, that's what we just said. Where does this distribution come from? This distribution. What's that? Entire population. So tell me about that distribution. So what's the random variable? 1,000 is not a random variable. Random variable is the thing for which we're going to get different values. No. What's that? No, a random variable is the thing that can take on many values. It's not a particular value. It's the thing we're measuring that can take on many values. So what thing of the population, we have a population of what that we're taking many values? Calcium intake. Calcium intake for adults. Calcium intake for adults. That has a population mean, so just the average of all calcium intake of all adults, or the ones in poverty, right? Below the poverty level, okay? So this population is below the poverty level, looking at the mean and standard deviation of those, okay? Doesn't have a sample size, it is the population. So we got to keep track of those two. We're keeping track of those two distributions, right? The sampling distribution, well, the original distribution is just the population. or the original distribution is looking at the random variable of calcium intake for these adults that fall below the poverty level. That distribution has a population mean and a population standard deviation. Then we're going to take samples of size 18, and we're going to look at the means of those samples of size 18, and that's going to form a distribution, the mean calcium intakes for samples of 18 adults, right? So now, can you do the problem? So when it says, what percentage of all samples of 18 have a mean calcium intake of at most 947, which distribution are you going to use and go to your z-table? Which distribution? The population distribution or the sampling distribution of means? Right, because we're asking about what percentage of all samples of size 18. So that's asking about the sampling distribution. So we need to find these values and then use our z-chart to get percentage, right? And percentage is equivalent to what in the z-chart? Area, right? Percentage is like area, and that's what the z-chart gives you. Can you finish the problem? Okay, good. Go for it. Yes, do it put it in your notes and put it on the sheet. Paper. It's for the paper. You now have 3 minutes to finish, and we're going on. 3 minutes. Just let me. Yeah, so exactly. We've done this 100 times in the last 3 weeks in different ways, shapes, and forms. This is not new. This is not new. So you need a mean and standard deviation, and you're looking for a percentage. You're looking for an area. Success? Show me. Okay, you have 2 minutes left. 2 minutes. And that's what we want? At most is to the left? Good job.
My brain didn't explode.
Hey, there you go.
I got 1.1. Sorry, negative 1.
Yes, no. 1 point negative 9.
Negative 1 point negative.
Oh yeah. Wait. 1.9.
Negative 1.
Alright. So you didn't see my face, so I probably did something wrong here.
Yeah.
What's the square root of 18?
Oh,
We're just finding the area.
yeah, sure.
The homework that we do.
I don't think this is a connection problem. We're just finding the area.
How much of extra credit are we gonna get? I like
Like
to do it.
each one. Well, but it's more about studying for the test than the extra credit, right? Each one 1% added to your test score. If you do all 3% added. So that's reasonable.
Great.
Oh, okay, good. I'm glad you think so.
Why did it get around it? Oh gosh.
Okay, we gotta move on.
Two different answers.
We gotta get to confidence intervals.
This would be mean though. This would be
Okay, let me just talk through this. I'll just talk through. I won't write. What is the mean of the sampling distribution of means? What is the mean? It's the same as the mean of the population. No, it's not 947.4. What is the mean of the sampling distribution of means? 1,000. It's the same as the mean of the population, the mean calcium intake. All right? What about the standard deviation of the sampling distribution? It's going to be smaller. When you take samples of size 18, it's going to be smaller than the standard deviation of the population. It's going to be smaller because you're taking samples of size 18. So we're going to take the, 188 and divide by square root of 18. Now you have a distribution. You have a distribution with a mean and a standard deviation, and you want all values of that distribution, less or greater than 947? Less than 947.4. And so we get a z-score, and we use the table, and the area under the curve is the percentage. Do we have to subtract from 100 or from 1? No, because the table always gives you areas to the left, right? Areas to the left, or percent less than that z-score. So that's finding the z-score using the table. That should be very comfortable with that. But the key is that you're using the right distribution. If you want a percentage of sample means, samples of size 18s, then you're going to use the sampling distribution. If you want a percentage of adults, then you're going to use the other distribution, right? Just the population distribution. If they said, what's the percentage of all adults that have a mean calcium intake of 947.7? Then you understand you'd use the population distribution, because that's the random variable, just the adult calcium intake. Okay, let's go on. Okay, so then we had these things called So then chapter 8 was about inferential statistics. Instead of having all samples of a certain size, we just take one sample of a certain size. And so then the mean of that one sample then becomes a point estimate for the population mean. Is it the population mean? No, because it's only one sample out of all the possible samples. If we have the distribution of all the samples, then the mean of that will be the population mean. Is everyone with me? Is everyone with me? If we have all the samples of a certain size and we take the mean, we know we get the mean of the population. But if we just have one sample of a certain size, which is much more realistic if you're doing a study, right? So we're going to look at all, so all sophomores on ASU campus. We're going to take a single sample, and then we're going to look at that single sample. And so the mean, so all sophomores and how many credit hours they've taken. That's the random variable, say. All sophomores at ASU, and the random variable is number of credit hours completed for sophomores. Number of credit hours completed. That's a random variable, right? We're going to go to Joe first. He's going to have a certain number of hours completed. Then Susie. Then Janice. Then Kurt. Each one is going to have a different number of hours completed, and that will make a distribution. So with that one sample, we're going to take the mean of that one sample. Is that the mean of the population? No, it's just one sample. But the mean of that is our best guess. It's what we call a point estimate. Okay, so then confidence intervals. I think we did that already. So then we can use the sampling distribution to obtain a confidence interval. So those confidence intervals that we found in chapter 8 came from sampling distribution. So let's do home improvement. Okay, home improvements. The following table displays the budgets in dollars of 45 randomly sampled home improvement jobs in the United States. Okay, so this implies two different distributions. What are the two different distributions that this problem implies? What's the first basic distribution that it implies? What's the random variable of the distribution? Cost of a home improvement job. For how many houses? No. Okay, but the random variable is the cost of home improvement for what? For one house at a time, right? So the distribution of the random variable is the cost of a home improvement job. And so we're going to go to the first house that had a home improvement job, and we're going to say what was the cost. Then we're going to go to the second house. What was the cost? Third house. What was the cost? That distribution is the population, going to form the population distribution of budget amounts. Budget amounts. Okay. Then there's another distribution implied here. What's the other distribution implied by this problem? Okay. So what about the 45 one? What distribution is it? Okay. Tell me about that distribution. Okay, so it's the mean budget amount for samples of size 45, right? The mean budget amount for samples of size 45. How many samples do we have of size 45? Do we have all of them? We have one sample of size 45. When we were talking about sampling distributions, we were assuming all possible samples. right, to make that distribution. But realistically, we're just going to take one sample, right? So we have one sample of size 45. There it is. Okay. So again, two distributions. Budget and mean budget, right? Budget for home improvement jobs, how much in dollars? And then the mean budget of size 45. So I want you to determine the sampling distribution, define the sampling distribution for budgets for samples of size 45. What is the sampling distribution for samples of size 45? What would define that? What would define the sample distribution for samples of size 45? Does that define a distribution, the mean and the standard deviation? Is that what defines a distribution? Yes. Yes. So you're going to find a mean. Populate, so it's the, what? A mean and a standard deviation of what about samples of size 45? We take samples of size 45 and we're going to find the mean of what? Yes, so we're going to find the mean budget amount, and then this is going to represent what? So we're going to find the mean budget amount for each sample of size 45, and that number is going to represent what? The mean of the means, the mean of all the means, right? And this is going to be the standard deviation of all the means. But we just have one sample, and we're going to infer what that is. We're going to infer what the population mean is and the standard deviation. So here's our we've got that distribution at work, and we have this distribution at work. Okay, so what is our point estimate? Our point estimate for the population mean is going to be what? How are we going to get the point estimate for the population mean? It's going to be the mean of the sample, right? The mean of the sample will give us our point estimate for the mean of the population. So we're going to take the sum of the data, right, and divide by. And what do we got? Anyone do it yet? 2885.53. Is it the population mean? It's the sample mean, and it's our best guess. It's our best guess at the population mean, right? It's all of the data we have. We only have 45, so that's the best we know. That. So how about, do you think that's a good estimate for the population mean, or could it be off? Or could it be off quite a bit? Or is it good? 45, big or small sample? Pretty big. Therefore, estimate is good or bad? Probably really good, right? 45 is a pretty good size sample, so this is probably a pretty good estimate. So we're going to build a confidence interval, right? So here's confidence intervals. We want a 95.44% confidence interval that the population mean for the population mean. What's going to be the center of that confidence interval? So we want to come up with some interval now of budget values so that we're 95% confident the actual population mean falls in that interval. Okay, so what's the center of that interval going to be? Yeah, so so this is our best guess at what the mean actually is, population mean actually is. So that's going to be the center of our interval. Oh, I really just hate what happened. There we go, I'm back. There we go, that's what I want. I need room. All right, can you make progress on this while I'm erasing? Progress on the confidence interval, 95% confidence interval. So we're going to have a confidence interval. It's going to be 95%. Basically, we've called this before the 95% confidence interval, but they're saying 95.44.
I trust this a lot more, so I'm just
So this number, 95% or 95.44%, should invoke a certain something else that we remember. What is it about 95% that's important? What is it? 2 standard deviations. Remember, 1 standard deviation was what percent of the data? It's about 68%. 2 standard deviations, 95%. 3 standard deviations, 99. Okay, so they're saying they want a confidence interval that encompasses 2 standard deviations. But 2 standard deviations of which distribution? The sampling distribution of size 45 or the population distribution? No, we're looking at samples of size 45. This is about samples of size 45, right? So that 2 standard deviation is 2 standard deviations in the sampling distribution of samples of size 45. So what is that standard deviation? Did they give us did they give us the population? 1350. Okay, so 1350. Is it 1350? Is that the standard deviation we're using to build this confidence interval? Nope. So then what is it? Divided by square root of 45. So if your confidence interval is based on a sample of size 45, you're going to use the standard deviation for the sampling distribution of size for samples of size 45. Just like in the hypothesis test, right? You always in the hypothesis test use the standard deviation based on the sample size. Okay, so what is that? What is that standard deviation? 201.25. Okay, so now we have 2885.53, and we want to build a confidence interval that's 2 of these up from here and 2 of these down from here. How much is 2 standard deviations above 2885.53? So you're going to take that number and do what? Add 2 of those, right? You're going to add 2 of these, or 2 times this. So this is going to be, we're going 2 standard deviations up. You got 3,000 what?
3,086.50.
80.
3,086.
No, 2 standard deviations. You added 1.
It's 3288.102.
I'll go with 3. And then 2 standard deviations below.
2,483.04.
So, interpret the confidence interval. Tell the person next to you, interpret the confidence interval. What does that interval? No, it's not 95% of the data lies between. That's not what confidence interval is about. Okay, anybody have a question? Ask a question for up to this point if you have a question. Is everyone clear on this? And what is the meaning of the interval?
I understood it, but it's just. I asked you a question because I don't know what you're asking me. When do we use the 95% is these four?
So you'll calculate 2 and then you'll.
That's not even outside of the confidence interval, right? Or not?
Because one of the
So we're the 1.96. So that
when you
Is-
by the standard deviation.
is 95.44. Is that 2? But 95 is 1.96. Is that what it is?
I think we just rounded to 2, right?
What's that?
You just rounded to 2, and that's why we multiply 2 times.
Yeah. So if it's I should say this. If it's 95.44, that is that's 2 standard deviations. So okay, but so 95. If you do 95%, that's where you get the 1.96, because it's a little bit less percent. So you're going to go up. You're not going to go quite out as far. So that's where the 1.96 comes from. But they're saying 95.44%. That's our 2 standard deviation value. Okay, interpret this. Interpret. Tabitha, can you interpret this?
Two standard deviations of the mean.
It's just 2 standard deviations from the mean, right?
Right. And what does it mean in terms of the problem? Gina, say it again. You said it perfectly.
We're 95.44% confident that the population mean lies within 2 standard deviations of the mean.
No. 90 lies between what?
95.44% confident that the population mean lies within 2 standard.
No. This is the interval. You're interpreting this. You're interpreting this. You're 95.44% confident that what? The population mean lies between 2483.04 and 3288. Yeah. So it's not wrong what you're saying, but we're interpreting these values, right? We're interpreting the confidence interval is this range of budgets. This range of budgets. Okay. What is the width of the interval? So what's the width of the confidence interval?
804.9.
And how do you know that?
Because they subtract the first one from the last one.
Yeah, so if you took the top of the interval minus the bottom of the interval and subtract, you get the full width of the interval. Now, what's the margin of error? Remember, margin of error. What's the margin of error? Half of that. It's the margin of error. Listen, everybody. It's how far in the value of the variable. So it'd be half the width of the confidence interval, or we already know what the number is. What is the margin of error? It was our 2. It's what you added to the 285.53 to get this number. So it'd be 2 times the margin of error was 2 times the 201. It's what you added to the point estimate to get the max value on the interval. Okay, so I've posted all 3 review sets. You get a little extra credit for as much of that as you do. You'll earn extra credit for your exam, but it's about studying. But like I said, those questions will be on the exam. Maybe I'll give you a situation. I'll ask you to interpret the situation in the framework of those questions, like we did today. Okay? So chapters 7, 8, and 9 are all covered on the exam Monday morning. I have office hours tomorrow morning from 9:30 to 11:30. If you can get started on your studying, come to my office for help. I could also make some time Friday to give you if you want to email me. Okay?